Okay, another thing we can do to represent vectors, there's all kinds of ways to do it. We've seen so far that we can do it with the component notation. We can represent the magnitude of them. Now, what if we want to write them like and kind of express that here is the x component and here's the y component? Well, here's how you do it. 1 times any number is just that number back. You have to remember that when you're looking at this. So what this is saying is if you want to have standard unit vectors, if I want to kind of think in terms of maybe writing something in a form of maybe a linear combination. Remember when we had 2x plus 3y equals 6 and negative 2x plus 6y is 42 or something. And we wanted to find their solution, we could add those vectors, we could add those equations together and solve using something called linear combination. Well, we can sort of do this with vectors too. We can make them look like that so we can add them together pretty easily. And so what we do is that the x component of the vector, if you want to think of it that way, which is really the horizontal component, this is this right here. This is kind of like our horizontal component here. It's really like our x. The x-axis is the horizontal axis. I'm just going to put component. See if I can hold the whole word component in there. The x-axis is our horizontal axis. So we would call this our horizontal component, but think of it as kind of like the x term. And then our y term kind of thing can be written this way. If you notice in this one, it's the y component that's 1 and the x is 0. Over here, the x was 1 and the y was 0. So this is our vertical component. It goes up and down like the y-axis goes up and down. Okay, so these are, if we want to break them apart into their components and combine them, we can do this and represent them in this form. And it gets confusing because there's so many different forms of vectors, so the notation can be confusing. Just remember, it's another way to write a vector. Okay? So we can turn it. What we do, let's say we have this vector here, and it has v1 is the x part and v2 is the y part. Well, what I can do is take the number that's here and put it out in front of the unit vector for the horizontal component, or like the x part, and I can write that x part this way, and this number just goes out front. And then I can do the same thing, the V2 part over here, let me maybe pick a purple color or something. That number can just go in front of the vertical component. So when you get done, what they end up doing is that they call this vertical component I, look up here where I circled in the red, I is equal to 1, 0. So they replace that with an I. Now this is not the imaginary I that you learn in Algebra 2. This is just a different notation. They're just using letters to show the x and y parts of vectors, and it gets confusing, okay? They call it I and J for vectors. Sorry. And then the J, if you look where I circled in blue, J is equal to 0, 1. So when you look down here where I've got this in purple, they just replace that with J and say V2 times J. So then you can put things together if you've got you know, 2 vectors, if you want to add them or subtract them. Let's look at an example so this gets clear. Okay, let's say that you want to write a linear combination of unit vectors. So let's let u be the vector with the initial point. Okay, so it's 2, negative 5. And the terminal point, negative 1, 3. This is going to put us through the ringer here. So we've got, this is our vector, this is our initial point, and terminal point. Actually, I'm not going to say u equals. These are the initial and terminal points. First of all, this is not in standard form. If you remember, and what we can do is put it in component form. And if we put it in component form, remember what we did was, for the x part, we're just going to subtract the 2 x's from each other, and for the y part, we're going to subtract the 2 y's from each other. Just remember, when you pick a point to start the subtraction with, you have to start with that point on the x part and on the y part. I'll just start with the second point. For instance, let me do the x's. I've got -1, and I'm going to subtract this 2. Okay? Now let's do the y part. Just choosing colors here. It doesn't really matter, I guess. I started with -1 the first time, so I got to start with that point the second time. I've got 3 minus -5. Remember, we're subtracting them. All right, that gives us -1 minus 2 is -3. 3 minus -5 would be 3 plus 5, or 8. All right, so that's what the vector looks like. All it means, if I want to put it in, if I want to write a linear combination of it, all I got to do is just put the i's and the j's with the pieces. So the linear combination form of it would be -3i plus 8j. It's that simple. It's just so confusing because there's so many terms in this section. I know as the teacher, I get confused and have to keep looking when I see the directions, and it's just it takes a while for all that to sink in. You don't do it every day, you forget it. So just remember, there's all these different ways to represent them. Okay, so let's look at an example of how I might use these linear combinations. Let's say they write the vectors in terms of linear combinations. U is -3i plus 8j. That looks a funny looking 8. And V is 2i minus j. So what if they want me to do 2u minus 3v? What do? Well, I take the vector u, and I'm just going to put -3i plus 8j in here, and I'm going to subtract 3 times vector v. So let me put vector v in here with the i's and the j's. This will make it easier to keep up with. All right, so now if I'm going to simplify this, I'm going to distribute. 2 times -3i is -6i, and 2 times 8i is 16j. Now I'm going to subtract, and because I got to subtract everything that comes out of it after it, let me put that in parentheses. 3 times 2i is 6i, and 3 times -j is -3j. All right, so I've still got some more cleanup to do, don't I? Because now I've got subtracting some things in parentheses. I'm going to have to change the signs on everything that comes after this subtraction sign. So remember, it's like distributing the negative sign. You can think of it as multiplying everything in there by -1 and adding it in. But I like to think of distributing the subtraction sign because it just helps me keep it straight. -6i, it was a 6i, the negative changes the sign. Here's another way to look at it, right? -6i, and a negative times a negative is a positive 3j. So if I want to clean this up and get my final answer, I have, for the I parts, we're just combining like terms here. -6i and -6i is -12i. And let's see, let's do a different color. 16j plus 3j is plus 19j. That's my answer when I have something like that. It's really not hard. It's just algebra is all it is. It's just that, the terminology can throw you sometimes, just trying to remember what you're supposed to do on a problem with the kind of directions like this. Okay, one of the reasons we wait to do direction angles until we get done with trigonometry is that there's things about it that it's helpful to remember. If you remember from trig, on the unit circle, here it comes again, you could rewrite this as, isn't on the unit circle the x value is equal to the cosine of whatever angle the ray is on the unit circle? So now we're going to look at these vectors as being placed at 0, 0 in standard position, and we're going to look at them as what angle does it make with the x-axis. So, and that's what the unit circle really does too. It's just another way of looking at our unit circle. Y was the sine of the angle that the ray on the unit circle, or in this case the vector in standard position, makes with the horizontal axis. So, I can also write this as cosine theta I plus sine theta j, because if I want to put it in the linear combination kind of form, I can do that. Okay, now theta, in this case, when we're thinking about it, we know what it is on the unit circle. It's the angle it makes with the x-axis in a positive direction. We're going to call this our direction angle. So all of our angles are going to be given in reference to the x-axis, just like they were in the unit circle. So this is our direction angle. So we can use this to actually find our angle. Okay. So if you think about it, let's say we've got a vector v. Let me just write in a different color. Let's say we got a vector v, and vector v is aj plus. I misspoke there. It's a times I plus b times j. That's our vector. We want to find the direction angle theta, and remember that's with reference to the positive x-axis. I wrote that in when I had it turned off while I was writing. I can do this. I can say the vector v is equal to the magnitude of the vector times cosine theta, sine theta. Remember, these are just, again, there are all these different ways we write vectors, and the x and y can actually be written as cosine theta, sine theta. And so, because v is equal to, okay, so that would be the magnitude of v times cosine theta. And I can put an I in there if I want to put it in component form, plus the magnitude of v times sine theta, and that would be my j. Okay. Now, if you remember something from trig, that remember we've got this. Okay, so I rewrote some statements that were on the other page. With those other statements, here's what we know. Don't we know from trig that the tangent of theta, of the angle, is the sine over the cosine? Okay. And so if we know that the sine of theta, if we know that we've got this part right here, we could put it over, I mean, those magnitudes would cancel out. The magnitudes don't matter. They're just like a scale factor in a way. And I did this. Isn't all this right here, isn't that just the number in front of the j? And isn't, let me pick a different color, isn't all this right here the number in front of the I? So I could put these two things on top of each other. The v's would cancel out. And what I end up with is, remember that red was equal to B, and the blue was equal to A. I'll try to write it in the colors. So we can find the tangent by just taking the number in front of the J and putting it over the number in front of the I. So it's B over A. We can find the tangent of the angle just by pulling off those coefficients and finding it that way. So it becomes pretty easy to find the direction angle of a vector. See if I can do this real quick. If I have the vector 3i plus 3j, then if I want to know the angle of it, I just have to remember that the tangent of the angle is the b over the a, and remember this is ai plus bj. So in this case, this b is 3, the a is also 3. Tangent of theta is equal 1. Do you remember what had a tangent of 1? It was 45 degrees, or pi over 4, however you need to write it. So you've got your angle right there. It's that easy to find the direction angle. I was trying to show you how they reasoned it out. But really, all you got to know is that you just put the b term over the a term, and that's the tangent. So you just do the inverse tangent. You say, what angle has that tangent ratio? So it would be secant tan on the calculator, and divide those things out. Let me see if I can write that before I run out of time. Secant tan b over a is going to give you the angle.